considering the constant electromagnetic field, the first field we will be considering is the constant electric field. Okay, so that branch of physics, that branch of electrodynamics we call as the electrostatics. Okay, another thing where we can consider the constant uniform magnetic fields. Okay, so that is the magnetostatics. Okay, so first we will be doing the electrostatics. In this case, so we are having the Maxwell's equations. So that's equal to 4 pi rho, and since these are the static fields, so curl of E is equal to 0. Okay, so it's curl free field. So these are the two Maxwell's equations which govern the electrostatics. Okay, so we can. So this is usual the Gauss divergence theorem, and this is actually, this means E has to be conservative. Okay, so we can express this E. So if you are having curl of some field equal to 0, then I can express it as the gradient, so of some potential phi. Okay, so phi is the, we can specify the electric field by this potential phi. If you remember, electric field due to both, we have in electrodynamics the electric field is given by this. Okay, you got my point? So both phi and A specify the electric field. If you are having, both x and t dependence of the field. Okay, so the complete electrodynamics. But we are considering only the static case. That's why it is only the phi we specify the electric field. Okay. So now let's substitute this E in the divergence theorem. Here in this very equation, what I am getting. So this equation yields me divergence of. So that's equal to 4 pi rho. So what it gives me? So it gives me nebula square rho is equal to minus 4 pi. Sorry, nebula square phi is equal to 4 pi. Okay? You got my point? So this equation we called the Poisson equation. Okay? So you are having, actually this is an inhomogeneous differential equation. So you are having sources on right hand side and rho specifies the phi. Okay? So in this very equation. Now if I am having vacuum, so let's take rho equal to 0, so that means you are in the vacuum. Okay? Or in the free space where there are no sources, there are no charges, this equation reduces to nebula square phi is equal to 0. So the goal of so this equation is known as Poisson equation, and this is known as what? Laplace equation. Okay, so the goal of electrostatics is to determine this phi. Okay, so you can determine phi if rho is known, or if rho is not there, you can still determine phi. Okay, so this is the goal of electrostatics. So if you know phi, you can figure out the electric field. Clear? So ultimately, you need to solve in electrostatics. You need to solve these kind of differential equations in certain situations. Let's assume, suppose if you are having a point charge, let's take for example point charge. Okay, so you can solve this differential equation for the point charge, okay, to figure out what is the potential, okay, or you can figure out what is the electric field. So the distribution is something spherically symmetric, is it? So now if you can figure out, let's think of a parallel plate capacitor. So you can figure out, you can solve these kind of equations just to figure out what is the electric field, let's say at the edges of the capacitor. Clear? So that's the given situation. Any arbitrary situation you are having, let's say you are having a point charge in front of a conducting plane. Yes. So you can calculate the electric field or you can calculate the potential. Okay. So this is the goal of the electrostatics. We'll be trying to solve, these kind of equations in different settings. Clear? So, but we'll start from we'll build up from the simplest examples. Clear? So we'll not directly invoke the solution of these differential equations. First we will build up from simple problems. Clear? Then we will go into the more complicated problems where we will directly solve these kind of equations. Okay? So now let's take, okay, since these are the differential equations, in order to solve a given differential equation, you need to know the boundary conditions or the initial conditions. Okay? Clear? So that means a given kind of situation. Okay. So we can also write, so this law, so let's take this differential equation. Okay. So we can convert it into an integral equation to a well-known Gauss divergence law. So E dot ds, that's equal to 4 pi q. Okay. So this q is the total charge enclosed by the surface S. Okay. So let's take you are having some surface S. Okay. An arbitrary surface. Inside this you are having actually q. Okay. So if it does not contain, if the surface does not have charge inside it, okay, if the total charge inside the surface is 0, then you can say this very object is equal to 0. So this is also known as the flux, electric flux. So the electric flux is simply what? So you can think it in terms of the number of lines passing through a given surface. Okay, so these things you already know. And another equation. You have this very equation minus del phi. Okay, so if you know the electric field, okay, if you know the potential, you can calculate the electric field. Okay, so you can calculate now phi from this very equation. So as minus, so you bring a charge, some test charge from infinity to a given point. Let's call that as r in a given point. Okay, let's write it this way, E dot dl. Okay, so you consider this way. Suppose if you are having some field, okay, in a given field, let's say, okay, you bring a test charge from infinity to this very point at any arbitrary point, let's say, okay, and you calculate what is the amount of work done here. So you bring a charge from infinity to a given point. So of this very thing, that specifies the potential. Clear? So now if you look at between 2 points, let's say A and B, you consider 2 points, let's say, finite points. So that defines the potential difference. Clear? So these are the two formulas we will use. So these things you already know. So this is actually the line integral. This specifies the direction along which you displace the charge. Clear? You know these things? So now let's take point charge. So simplest example is the point charge. Okay, so if you let's take a positive point charge. So if you look at this very charge, let's call this as a plus q. So how the electric lines of force will go? Outwards. So at any point, so you'll be having like this thing. So in other words, you are having actually the spherical symmetry for the point charge. Clear? So for point charge, you are having actually the spherically symmetric. So that means the electric field at a given point is radially directed outwards. Okay. So the electric field, the direction of the electric field is where? So along the radius vector to the point at which you are observing the field. Okay. So it does not depend on any kind of angle. Clear? So in that case, so you are having this very law. So you can choose actually a surface, so what we call as a Gaussian surface, let's say. So of something radius r. Okay. So then you calculate the electric field. So that's 4 pi q. So the Gaussian surface actually should enclose the charge. So that's q. So since E and ds, so ds is actually any element on this very surface. So E and ds are in the same direction. So you can calculate now. So it's E times 4 pi r square. So I should say capital R. Okay. So r is the radius. So that's 4 pi q. So E is equal to q by So this is the electric field. Okay, so the direction is along. So in as a vector, you can write it as like this thing, Q by R cube. Okay, vector R. Okay. So what is the potential? So the potential you can calculate it. It is simply Q by. Okay. So these are the simple things you already know. Now let's say if you are having a system of charges somewhere. Let's say you are having system of charges here. Okay, let's say Q1, Q2, Q3 and so on. Let's say Qn, and you try to calculate, let's say at a point P, you try to calculate what is the field due to all these charges. Or how you'll do? You'll just apply the superposition principle, okay, and calculate the field due to individual charges. In other words, I can calculate the potential, so that also follows the superposition principle. So I can write it as like this in Q1 divided by, let's say, R1 plus Q2 by R2 plus dash 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 plus Qn by R. So that's equal to, let's say, summation of A Q by. Okay, while R1 is, okay, so that distance to the point P, okay, and R2 is the distance from charge Q2 to the point P, and so on. Clear? So this is actually the superposition principle. Now if you are having the charge instead of the point charges, now let's assume you are having a volume charge distribution. Okay, let's consider you are having somewhere volume charge distribution defined by some density rho, such that you can calculate the total charge Q is equal to integral rho dV. Okay, I'm going quickly because these things you already know. Okay, so then I can calculate the potential this way. So you write rho by R and dV. Okay, so this is how you calculate it. Okay, so let me write that formula explicitly. So you are having, let's say, some volume charge distribution, and you take some volume element, and let's write that as dV prime. Okay. Okay, let me define my coordinate system. So this is, let's say, R prime, and at the point P, let's call this as R vector. So this difference defines your vector R, that's equal to R minus R prime. Clear? So then I can write this potential phi at the point R, okay, at here. So that's equal to rho of R prime, because this density, you take the small element in this dV prime, okay, divided by R, that's actually R minus R prime, okay, D3. So this is actually the potential. Okay, now in deriving this kind of formula, so what you actually are assuming there is actually an assumption which you are actually not applying directly. So you take that assumption that field vanishes at the boundary, okay, or the potential vanishes at the boundary. Clear? So okay, you know what is the potential due to a point charge? So it's Q by R, is it? So what happens to the potential at the boundary? Let's say if boundary is stretched to infinity, it goes to 0, is it? So what about the electric field? That again goes to 0, is it? Because we assume there are no charges at the boundary. Clear? So if my boundary extends to, let's say, infinity, okay, so then I assume there are no charges or currents at infinity, is it? So in that sense, my potential, it goes to 0. Okay, so this is a basic assumption for this kind of formula. But we'll see, we'll be having a problem. Okay, when we can, okay, let's consider, okay, I will do that explicitly, that example. Think of the line charge. Okay, let's say you are having a line charge that extends to infinity, is it? Okay, you know the linear charge density? Okay, so you consider a line charge density, okay, that extends to infinity, from minus infinity to plus infinity. Or in other words, you think of an infinitely long conductor, okay, or infinitely long wire which carries charge density distributed uniformly throughout the wire, is it? So what happens then, I mean at the boundary then, So since the conductor or this wire extends to infinity, is it? And it carries charge still there, is it? So in that case, potential will not be zero. Clear? You got my point?
Yes, sir.
So that means the assumption what I am saying in this very formula, the potential goes to zero at boundary, is it? Or think of the infinite sheet containing the suppose surface charge density, is it? Okay, you are having a sheet of paper, let's say it extends to infinity and it carries charge density, is it? So you still have actually charge at infinity, is it? Got my point? So you will be having certain kind of situations where you will see this kind of assumption does not hold. Okay, in that case you need to relax the assumption. Okay, you can redefine your, let's say, reference point. Okay, you can say, I mean, you can choose, let's say the potential is constant or uniform at the boundary. Okay, you can, instead of going to zero, you can say, let's assume potential goes, okay, potential value is a constant at the boundary. Okay, instead of zero, it is constant. Clear? Because at the boundary, I am having charges. Clear? So we'll see this kind of example explicitly in a moment. Okay. Okay, so if you are now given, let's say, electric field, you need to calculate the charge. Okay, so let's take that kind of example. So if electric field is given, so yes, one more point. Okay, let's take this very formula again. So you are having, let's say, this nebula square phi is equal to minus 4 pi rho. Clear? So take a point charge. Let's take a point charge Q. Okay. So what is the density for the point charge? Delta bar. Is it? Is this the density? Clear? So this is the I mean charge density due to a point charge. Okay. Okay. So now what is phi? I have figured out for point charge. What is phi? Q by R. Is that true? Okay. So that means nebula square Q by R, it's equal to minus 4 pi Q delta of R. Clear? So what it yields me? Nebula square acting on 1 by R, it gives me 4 pi delta of R. So this is another way to define the delta function. Okay. So we call this function, this 1 by R, the Green's function, corresponding to the potential, corresponding to the Coulomb potential. Okay. So I will do these things in detail. So, or in other words, let's say, or I can write nebula square 1 divided by magnitude of R minus R prime. Okay, and differentiation is with respect to this R, that's equal to minus 4 pi delta of R minus. Clear? So this is for the point charge. Got it? Okay. Any question till now? Okay, so let's take an example. Let's take the second example. So I am having an electric field due to certain, let me write the electric field due to some charge distribution. It is given by Q vector R by R raised power A. Okay, where A is a real constant. Okay, E is given. Clear? So E is given to you, and you are supposed to calculate what is the charge density. Okay, or what is the charge that gives you what is the amount of charge that gives you this kind of electric field. Clear? And try to calculate the potential. So much. So in the previous situation for the point charge, what was given? Charge was given. The amount of charge was given, and you calculated what? Electric field and the potential. Now the electric field is given, and you are supposed to calculate the charge. Okay, and we will then calculate the potential as well. So first thing you note, so this is actually the curl free. So curl of E is equal to 0. Okay, you can check it. So if curl of E is equal to 0, so that means you can write the electric field in terms of what? minus nabla phi. And so this will imply actually, so phi is equal to minus infinity, okay, so infinity to some point r, okay, E dot here, okay, clear? So now let's calculate first the charge. So let's calculate the divergence of E, okay. So look at this very distribution. Since curl of A is equal to 0, if you see, look at this very formula. So it does not contain any angles. Is it true?
Yes,
Okay, let's check. Let's take A is equal to 3 for the time being. Okay, so what it is? It is simply Q by R square, is it? So it means it is spherically symmetric. Samajh? Since it does not depend on any angular coordinate, so it only depends on the radial coordinate. So you can think this as actually spherically symmetric, is it? So when I write the divergence of E, so I can expand this divergence in terms of spherical polar coordinates. Clear? Or samajh aawa? Okay. So I will write it as like this thing, Q del dot vector R by R is for E. Okay, so in spherical polar coordinates, how I write this divergence? So it's simply partial by part, okay? Partial R, okay? Anybody? Anybody? So it's like this thing. Just tell me. So it will be simply. Oh, sorry. So let's write it in this way. So let's write it in this way. Instead of expanding it into spherical polar coordinates, so I'll consider this as a scalar function 1 by RA. So it's something, let me write divergence of 1 by R is for A and vector R, like this thing. Okay, so let's write the formula. Anybody knows the formula? So let me write in detail. So if you are having some function, so this is a scalar function, and then you are having a vector. How you evaluate this thing? Anybody? How you work it out? So it is V dot gradient of F, then plus. Yes. Yes. Gradient of E कहाँ से आ जाएगा? F into divergence. Because it's a scalar quantity. Divergence is a scalar quantity. So it will be simply V dot. So this is a vector. So dot product of two vectors is a scalar quantity. Divergence is a vector quantity. Clear? So now let's work it out. So what is that equal to? 1 is, so it will be V dot. So it is R dot gradient of 1 by R is for A plus 1 by R is for A divergence of vector R. Clear? So what is that equal to? Can anybody tell me? So it is R dot. Anybody? What is differentiation of 1 by R is for A? A minus 1. Okay. So, but I can put it like this way. R divided by R raised power A plus 2. Can I write? Can I write? So, anything more to it? So, there will be a minus sign. Now tell me what is divergence of R? So, it is 3. Is it true? Divergence of vector R is what? It's equal to 3. So what it is? So Q R dot R is R square. So it's minus R square divided by R raised for A plus 2 plus 3 divided by R raised for A. So how much is that? Q into 3 minus. So I think there should be an A here. So there should be some A here. So 3 minus A divided by R. Clear? Everybody followed it? So what this is divergence of E. We know divergence of E is how much? So it is 4 pi rho. Clear? So now let's compare the two. So it means, so that's Q into 3 minus A by R raised for A. Okay, so what rho is that? So which implies rho is equal to Q by 4 pi 3 minus A divided by R raised to A. So this is the charge density. Clear? So this is the charge density. If you know the charge density, you can calculate what? Charge. Okay. So let's calculate charge within the radius of R, capital R. Let's assume. Okay. So let's calculate charge within the radius R. So this will be assignment to you. Okay. So it will be Q integral of dV, rho dV. Okay. So this is spherical symmetric, is it? Because it's a function of only R. Okay, so what you need to do? You simply convert it to the spherical polar coordinates. So it will be simply 4 pi. Let's say instead of 0 to infinity, 0 to R you will calculate. So R square and dr, and then this very charge Q by 4 pi 3 minus A divided by R is for A. Calculate this thing. So you get the total charge within the radius R, capital R. Okay. Okay. So let's calculate now the potential. So let's calculate the potential. So what is our potential now? Phi of R. So it's minus from infinity to a given point. E dot dl, let's say. So how much is that? Minus, okay, infinity to R. So what is E? What is the electric field? Q, let me write it as R prime as a dummy variable, okay, because R is here as the limit of the integration. So R prime raised for A. Then you are having dl, so it will be simply what? Anybody? What it will be? What dl is? What is the direction of dl? Along which coordinate it is? Huh? Yes. It is in the direction of the field, is it? It's actually along the radial coordinate, is it? So it will be simply dr, r dot dr prime. Clear? So it will be like this thing. So how much is that? So it's simply minus q 0 to r. Okay. So it will be simply dr prime by r raised power a minus 1. Okay, because the direction is same. Okay, so cos of theta is equal to 1. So it will be simply r dr. So r and so it will be a minus 1. Now tell me what is the difference? Okay, integration of this very object. Also with the integration of 1 by r is a minus 1. Just tell me. Okay. So just do it on your paper. So I'll write the result here. So this is the potential. So here A is not equal to 2 in this way. The reason being simple, if I take A is equal to 2, so this is the resultant. So if I take A is equal to 2, so this diverges, is it? So there is a divergence for equal to 2. So that means I need to solve this kind of integral separately for A is equal to 2. Got it? So let's write that. So I'll write this phi of R, okay. Now my result, it is for A is equal to 2, it is simply minus, okay, infinity to R. So what is E? So it will be simply Q dr prime divided by R prime. So what is the integration of 1 by R? Log of R, okay. So it is simply minus Q natural log of R, okay. R prime and your infinity and R. Now you look here in for A is equal to 2, what happens to the potential? So you are having a first term is Q natural log of R, is it? And another is an infinite constant. Clear? Because log of infinity is what? It diverges. Got it? So the potential for A is equal to 2 diverges. Okay, so there is a contribution. One is the logarithmic contribution, and then you are having actually an infinite constant. Now, so it's actually a puzzling result, but as you know, potential is not an observable quantity. Okay, what is an observable quantity? Potential difference. Okay, so as such, potential is not an observable quantity. It's only actually the difference between two potentials that is an observable quantity. That's actually the electric field, or the potential difference. What you know, potential gradient. Clear? Okay, so if I calculate now the potential difference between the two, between the 2 points, so this infinity will be replaced with, let's say, R1 to R2, okay? So in that case, it will be simply natural log of R1 by R2, clear? It will be a finite number. So summation, an observable quantity is always a finite number. You should not get a diverging result for an observable quantity. You can throw away this infinite constant because we know, so potential can be defined arbitrarily, is it? So this is the problem what I was saying in a moment when we wrote the formula for the potential, is it? So potential vanishes at the infinity, is it? So but if you go to the infinity, what happens? So it is always in physics we always encounter such kind of problems. In that case, what we need to do, we need to simply regularize the integrals. Okay, we need to redefine the integrals such that you can extract some finite result, some meaningful result. Okay, so we have extracted actually one meaningful part, so that is this kind of behavior. Okay, so you are having a logarithmic contribution to the potential plus some constant which is not useful to us. Okay, clear? So now let's take another example. So let's take third example, Yukawa potential, or we call it as a screen Coulomb potential. Okay, so screening Coulomb. Okay, if you look at potential, okay, phi is equal to, let's say, Q by R, is it? Okay, so this is actually the long range potential. Okay, if you take, let's say, R tends to infinity, you still have some non-zero. Let's say if R is very large, you can still have what? A non-zero potential, a finite non-zero potential. Clear? Only at infinity, when you are sufficiently far away from, let's say, the source, then you can say the potential is zero. But at larger distance, not that sufficiently large, but a good large distance, you can think, let's say you are having a point charge, at certain large distance, you will still feel what? The potential. Okay? Now, so this is the long range interaction. The Coulomb interaction or the electromagnetic interaction, it's always long range in nature. Okay? So, if you screen it, this kind of potential, you put a finite range instead of the long range, okay? Rather the infinite range, you make it actually the finite range, okay, such that potential goes to zero or potential drops sufficiently at certain point. Clear? So this way, let's think it this way, this kind of potential. Let's think of a sodium atom. Okay, so you are having the inner electrons. Okay, then you are having one electron in the outer shell. Is it? So you are having 11 electrons. So you are having 2 here and 8 here. Is it? So 1 is here. Okay? So how much potential this sees, how much charge this sees, this electron? So you can think it sees the effective charge or effective potential due to this very core. Is it? Clear? Because it is the completely shell. So how much is that? How much is that? Or in other words, it's some, okay, let's think, let's forget of these electrons. If these electrons were not there, these 10 electrons, it can see simply this nucleus as the point charge, is it? How much point it is? It will carry 11 charges. So that means 11 units we can consider. So it is a bigger charge, but this electron will see this entire charge, is it? So but if you take these electrons into account now, so what will happen? So because of the Coulomb attraction and so it will see actually the effective charge arising from here. So in other words, this charge gets screened by all these kind of electrons. So we can put it this way: the potential what this electron can observe due to this very nucleus is screened by the other charges. Is it? So that means there is some sort of, I mean, some range, some cutoff arises here. Okay, that kind of screened charge or screened potential we call as the Yukawa potential. Let's call Q as the amount of charge and R is the radius. We put it as an exponential cutoff like this way. Okay. Okay. So that means if you are having R is equal to mu, so it drops by 1 by E time, is it? So that means it drops sufficiently at that very point. Clear? So this mu gives me 1 by mu gives you the range of the potential. Okay. So sometimes we call it as 1 by mu square as the mass of the particle. So, but I will not take that definition for the time being. Okay, you can consider simply it as the range of the potential. Okay. So now potential is given. So you need to calculate the electric field and what is the charge. Okay, what is the charge density that produces this kind of potential. So what I should get. So this is a screening potential. I should get. Okay, if this is not screening potential, and I ask you what is the charge, what is the charge density, you can simply say it is the point charge density, is it? Now my potential is screened, so and I ask you what is the charge density corresponding to the screening potential. Okay, you can say, so it must contain contributions from the point charge density and some another thing which represents the screening of the charge, is it? So this is an intuitive picture of this, I mean, calculation. So now let's calculate. Okay, so let's calculate the electric field. So this is actually the spherically symmetric potential. So let's calculate the electric field. So you are having electric field as minus gradient of phi in spherical polar coordinates. Okay, spherical polar coordinates. How you write? Anybody? So it is unit vector r partial by partial r of phi. So that's q e raised power minus mu r by r. Okay, let me write small r. Let me write small r. Because I'm using small r here. Okay, how much is that? So it's q unit vector r, okay, by r square into 1 plus mu r, okay, e raised power minus mu. Okay, so this is the electric field. So you just differentiate it, you will get this result. Now let's put mu is equal to 0. Okay, if you put mu equal to 0, so if mu tends to 0, what you will get? E is equal to simply q by r square unit vector r. So that is the Coulomb potential or the electric field due to the point charge. Clear? So now if I need to calculate what is the charge density corresponding to it, so I will simply calculate the divergence of E. So how is that? Okay. So how I write the divergence? So it is Q divergence of, okay, what is our E? Tell me. So it is, okay, let me write this as, so you can write it as vector r by r cube. So vector r by r cube. So that is same as unit vector r by r square. Okay, 1 plus mu r e raised to mu r. Okay. So let's write. So it is divergence of, okay, this vector r by r cube into 1 plus mu r e raised to power mu r plus then r divided by r cube dot of gradient of 1 plus mu r. So this formula we have used it earlier. Huh? So clear? So this is the formula we have used it. Okay, I have considered this entire object. Now, anybody? So I know. Okay, gradient of 1 by r, that's actually equal to minus vector r by r cube. Is it true? What is the differentiation of 1 by r? That's minus 1 by r square. So I have put a vector r. Since it's a gradient, so it will be a unit vector. So it will be unit vector r by r square. I have put a vector r and divide by r cube. Clear? Okay. So let's use this very result. So for this thing, so therefore I can write this divergence of E is equal to Q into del dot minus gradient of 1 by r. Okay, like this way. Okay, instead of this r by r cube, I have put it this way because I know I have just derived the result. What is the del square acting on 1 by r? That's a Dirac delta function, is it? Is that true? Laplace square acting on 1 by r is Dirac delta function. That's why I have put it in this fashion. 1 plus mu r e raised to minus mu r plus, so it is vector, okay, I will write it simply as a unit vector now. So unit vector r by r square here. So this will return dot. So this I can use now in the spherical polar coordinate. That's simply r partial by partial r into 1 plus mu r e raised to minus mu. Clear? So this is equal to q. So this will be minus Laplace square 1 by r. Let me put each term together. I mean step by step. Okay. So these are the things. Okay. Can anybody tell me? So r dot r. So it is simply 1 by r square. So anybody can tell me the differentiation of this thing? Just tell me the differentiation of this very object. So it will be simply. Anybody? So it's simply okay. So just I will put the result directly. So it is simply minus mu square by r square e raised to minus mu. Okay. So it is a differentiation. You just need to differentiate by parts. Okay. So this object is equal to q. So this object is equal to 4 pi delta of r. 1 plus mu r e raised to minus mu r minus mu square by r square e raised to. Okay. Okay, now we will use this kind of formula, delta x into f of x, that's equal to delta x f of 0. Is that true? So you have to evaluate f of x at x equal to 0. True? So now let's evaluate. So this very object, so this is the f of x. Okay? So a delta of x multiplied by f of x. So you need to evaluate it at r equal to 0. So when you put r equal to 0, this goes to 0, this equal to 1. So therefore, I am having this del dot E, it's equal to q 4 pi delta of r. It's actually a three-dimensional delta function, I should say, because r is the magnitude of a 3 vector. So minus mu square by r square. Okay? Everybody got it? Everybody followed it? Okay. So now that's equal to 4 pi rho, because del dot E is equal to 4 pi rho. So it implies therefore rho is equal to, okay, you divide this quantity by 4 pi, so it is simply q delta of r minus mu square divided by 4 pi r square e raised to minus mu. Okay? So now this is actually the screener charge density. Okay? Got it? Now look here, if mu is equal to 0, we have just seen if I put mu equal to 0, it reduces to the point charge. The results of the point charge we recover. Let's put mu equal to 0, so this term goes to 0. What you are having? charge density of the point charge. समझ आवा? So that means your point, this charge density is actually screen, okay, and the net charge is actually, so the point charge minus this much amount. Clear? समझ आवा? So now let's say you can actually calculate it within the radius, let's say r, okay. So you just calculate it. So let's say within a radius r. Let's think within radius, or you can think within bow radius. First bow radius. Let's think within radius r. So what is the total charge? So it is integral rho dv. So that's equal to 4 pi. So 4 pi comes from the solid angle 0 to r. Instead of infinity, you put 0 to r. So what you are having then? So what is rho? So it is rho of r square dr. Okay? Then you need, okay, so let's calculate it. Is it clear? Is it true? Is there any problem? What I should get? So, delta GRN. Is it true? What I? Is there any problem? Is there any problem? Is there any problem with this formula? Huh? So do you think? So what you should get? Let's put mu equal to 0. You should get actually. Oh, wait a second. So it's something, okay, so it's like this. So rho, so it will be simply Q delta of R integrating over the entire volume, integrating over the volume. So volume of the radius R minus mu square by 4 pi integration over volume dr, okay, of e raised for minus mu R divided by R square. So this is the result. So you are having this as Q minus this, okay. So that's equal to Q minus mu square, because integration of delta function, that's equal to 1. So this will be equal to, so let's evaluate. So it is 4 pi 0 to r square dr, okay. Then you are having e raised power minus mu r by r square. So this r square cancels. So how much is that? Q minus mu square. So what is the integration of this very thing? So exponential. So it is e raised power minus mu r minus 1 divided by minus 1. Okay, so that's equal to Q plus, okay, mu into e raised power minus mu r minus 1. So this is actually the amount of charge you get. समझ आया? So this is, okay, so if you put mu equal to 0, so you will get total charge at Q. Clear? Okay, if let's say the radius of the circle, what we are assuming, so since we have considered the radius r here, so if you take this r tends to infinity, so what will happen to this thing? So this will go to 0, is it? So in that case, so what is our total charge? Q minus mu for r tends to infinity. So समझ आया? Got it? Okay, so now let's take the hydrogen atom. Okay, so what is the charge density for the ground for an electron in the ground state of the hydrogen atom? So it is the fourth problem. For an electron in the ground state of hydrogen atom. So this is just these are the warm-up exercises. So you should know how to apply these things. So what is the charge density? Okay, so let's check how many knows. What is the charge density of an electron in the ground state of the hydrogen atom? Okay, what is the wave function? The wave function for the s orbital? Or what is the wave function of an electron in the ground state of the hydrogen atom? What is its form? Any idea? Obviously it is spherically symmetric, but what is that? How much is that? So psi is equal to 1 divided by root of pi a cube e raised to power minus r by a, is it? Where a is the Bohr radius. You people know it? So now tell me what would be the charge density. I know the wave function, what would be the charge density? So I need to multiply E psi star psi. So this will give you the charge density in the ground state of the hydrogen atom. How much is that? 1 divided by pi a cube e raised to twice r by. Okay. So let's take. So I'll use Q as a charge on electron. So it's rho of R Q by pi a cube e raised to, because I'm using Q. Okay, Q is magnitude of charge. Okay, A is equal to Bohr radius. How much is Bohr radius? Okay, 0.51 Armstrong. Is it 0.51 or 5321? Huh? So how much is it correct? 0.51? Huh? No. Huh? 0.5?
529.
53? Just check it. Check it. Huh? So you can calculate how much charge should be there. Tell me. So check charge. Okay. If I integrate rho dV, so it should be simply equal to what? Q. Q is the charge on the electron. Okay. Okay. So let's calculate the electric field due to this very charge density. So I am having A dot ds, so that's equal to 4 pi q. So q is the enclosure charge. Okay, so let's say you are having this as the electron cloud. Okay, so this is the first orbital. So I will consider a Gaussian surface of radius, let's say r. Okay, so much. So once you if you are having any charge distribution, you always choose a Gaussian surface. Okay, to evaluate the electric fields. You cannot do it without choosing a surface. Okay. And the Gaussian surface should enclose the charge. Okay, so I am taking this Q, it is the charge enclosure. How much is that? Since it is spherically symmetric, so you are having E into 4 pi, let's call it as r square. Okay, let me write small r. Let's write this as a small r. After it is small r. Okay, so how much is the charge enclosed? So it is 4 pi integration over the volume d3r over 1. Clear? Is this the case? So this is the amount of charge. So that's equal to 4 pi. So d3r prime. So what is rho of r prime? So it's q divided by pi a cube e raised power minus twice r prime by a. So let's write it as 4 pi. So it will be simply, okay, e is equal to, that's right, that's equal to q, anybody? Pi a cube, so you are having r square as well. So then you, okay, integrate it where? So there will be a solid angle, let's call that, okay, the amount of solid angle is 4 pi. So then you integrate from 0 to r on the radius of this very Gaussian surface. So br multiplied by r square, okay, e raised to minus 2s. So let's call this as prime. Okay. So you need to evaluate this kind of integral. This is very simple integral. So it will be equal to, so the electric field I get. So this is simple integral. I am just showing. So the electric field I will get as q by r square into 1 minus 1 plus twice r by a plus twice r square by a square e raised power minus twice r by a. Okay. So this is the electric field. If I put, let's say, a unit vector, so that will give me the direction. Similarly, you can calculate now the potential. Electric field you have calculated. So my infinity to r. So E dot, simply E dot dr. So let's call it as dr prime. So you need to integrate this very formula. So let me write it. So it's infinity to r. Q, let's call that q outside. So it will be simply dr into 1 by r square into 1 minus 1 plus. So let's call this as a prime because it's a dummy variable. 2r prime by a is 2r prime square by a square. So you need to integrate this very object, what you'll get. So let me write it. So you'll get phi of r is equal to q by r 1 minus 1 plus r by a raised power minus 2. So this is the potential due to what? So these are the simplest charge distributions we have considered. We have calculated the fields and in certain situations we have calculated the charge density. Okay. So now let's take. Okay. So let's stop here. Let's